Jnanam Paramam Dheyam. Knowledge is supreme.
So, given a set S contained in R and L of S is a vector space. Right. So, let us go back and write that example which I just now said. So, examples. So, let us take S equal to x naught belonging to R 2, right. Then what was L S? I should, S is a single vector x naught, it is a set. So, it is x naught, I should write it properly. It is a set consisting of only one element, right, x naught. So, how will you form linear combinations of it? Only one vector to choose, multiply by a scalar. So, what is L S? Alpha times alpha belonging to R. Is that okay? That is the only combination possible. So, that was line through origin, right. Is it okay? Okay. Let us look at a second example. So, let us look at S to be a set. Let me take some particular vectors. Okay, this is this you have all have done it. Let us look at 1 0 and 0 1 in R 2. So, I am taking two vectors 1 0 and 0 1, right. So, what is L S? It should be alpha times 1 0 plus beta times 0 1, where alpha and beta both belong to R, right, linear combinations. If I take alpha equal to 0, I am only taking one of them. If I take beta equal to 0, then I am taking only the first one. If both are non-zero, I am taking a linear combination of both. So, I can, by choosing alpha and beta suitably, I can take one of them or either of them or none of them, but none of them means what? Alpha is not none of them, it should be the 0. So, 0 vector comes inside it, right. Is it okay? What is that equal to? Let us write, simplify. So, that is alpha 0 plus 0 beta, where alpha and beta both belong to R. And what is that? So, what is that? So, that is equal to alpha beta, alpha and beta belonging to R, right. What is this? If alpha beta are arbitrary, what is this equal to? This is precisely R 2, the whole plane, right. Alpha and beta are arbitrary. So, every vector in R 2, I can choose it and make it equal to this, right. So, L S is equal to R 2 for S equal to 1 0 0 1, right. Do you recognize this already? Do you recognize what I am doing? I am not doing anything new. It only says what is 1 0? So, this is this vector. What is 0 1? That is that vector. So, that is what you call, normally you call it as I, you call it this as j. What is every vector? Some alpha x I plus beta of j, right. So, that is precisely what we have done in a different language, that is all, right. So, that means the linear span of these two vectors is equal to whole of R 2, right. let us take one more example in this to understand what we are doing. So, let us take the set S to be equal to, I am taking again 1 0, 0 1, and let me take it 1 1, 3 vectors now in R 2, right. I have taken 3 vectors in R 2. What is L S? S, okay. S is a subset of R 2, this set is a subset of R 2, right. So, if call this as V 1, call this as V 2 and call this as V 3, just for the sake of it, instead of writing every time matrix. So, V 1, V 2, V 3, they belong to S, which is a subset of R 2. So, what does that mean? That means V 1, V 2, V 3 also belong to R 3, right. It belongs to the subset, so belong to the whole space anyway, right, as a set. If something is element of a subset, it is also element of the whole thing. So, V 1, V 2, V 3 are elements in S, they are also elements of R 2, but that implies where is alpha V 1 plus beta V 2 plus gamma V 3? Where is that? That is again in R 3, right. If you take 3 vectors or any number of vectors and take linear combinations, that is again going to be an element in, is again a vector, right. Go on adding. So, you can add first 2 and add the next one, again you will stay in R 2, right. So, that means what? What does this imply? This implies, but this, where is this element? This is a linear combination of elements of S. So, that implies L of S is a subset of R 3. L of S is a subset of R 3. You can't go outside R 3. You will be inside R 3 only. Everything is R 2 going on, right? R 2. Everything is in R 2. Linear combination of adding 2 vectors will again be in R 2. So, you will stay in R 2. So, L of S is a subset of R 2, right. We want to know, can we say something more about it? Okay. So, let us write. So, L S, we want to find out what it is. Okay. So, let us note one thing. Let us look at V 3. What is V 3? That is 1 1, right. V 1 is 1 0, V 2 is 0 1. I can write this as 1 0 plus 0 1, right, and that is same as V 1 plus V 2, right. That means, this V 3 is already a linear combination of V 1 and V 2. So, this implies, what does this mean? That means, linear span of S is same as the linear span of V 1 and V 2. I do not need V 3, because V 3 itself is a combination of V 1 and V 2, right. So, I can get V 3 from V 1 and V 2 by linear combination. So, again by taking linear combination, I do not have to repeat the process of adding V 3 again, there is no need for that. Is it clear to everybody? Yes, or still not clear? Let me expand a bit more. So, let us look at alpha V 1 plus beta V 2 plus gamma V 3, that is an element of L of S, right. So, what is that equal to? It is alpha V 1 plus beta V 2 plus what is V 3? Is V 1 plus V 2. So, it is gamma times V 1 plus V 2. So, what is that equal to? It is alpha plus gamma of V 1 plus beta plus gamma of V 2. So, any linear combination of V 1, V 2, V 3 is actually a linear combination of V 1, V 2 only, right. I can express it as linear combination. So, what does that imply? That implies the linear span of S, which was V 1, V 2, V 3, 3 vectors, is same as the linear span of the first 2 only, right. So, that means V 3 was redundant in finding what is the linear span of the set S, right, because one of them was already linear combination, right. So, that means what, given a set of vectors, if you take a linear span of them, right, then probably some of the vectors you can cut down, remove them, right. You can get a smaller subset of the original set which will span the same thing, and probably you can go on cutting, but can you remove everything? No, you can't remove everything, there has to be something, right. So, that means what? That means given a set S and a linear span of it, possibly you can have a subset of it which gives the same span, but there should be something called minimal, probably the smallest subset which will give me that, right. And idea should be like in this example we have done it, we should be trying to do it every time, right. So, that motivates a definition what is called the basis of a vector space. So, let us define. Okay. So, let us take, let V contained in R n be a vector space, and be a subset of V such that 1, the span of B is equal to V. V is a vector space which is a span of B, right. Is it okay? Second property I want to say is, I want to minimize, I want to say this is the smallest, that means how should I write it? So, if B 0 is a subset of B 0 is a subset of, I want to say it is the smallest. So, I shall write. So, if is a vector space is that, and okay, I think this is a better way. There is, let me write English first, there is no subset, probably one should say proper subset of B which spans V. That means what? That means what? That means there does not exist B naught a proper subset of B such that linear span of B naught is equal to linear span of B which is equal to V. 1, B spans V, right, the set B spans, and from B I should not be able to cut down something, so that the smaller thing also spans. So, this is the property of B I am saying, such a B is called a basis of V. Such a B is called a basis of the vector space B. That means what? So, once again let us try to understand this concept. V is a set, V is a vector space, and we are saying a set B is a basis, means what? It should have two properties. One, the span of B should be V, every vector should be a finite linear combination of elements from that set B, right, that is one. And from B I should not be able to cut down something and make it smaller and still getting the all of V. That means no proper subset of B will span the vector space V. Is it clear, or shall I explain? There is B is some subset of V, and when I take linear combinations I get V, but this B I cannot shrink it smaller, so that when I take linear combination I get still the whole thing again, that should not be possible. That means B is in some sense the smallest set which generates, right, smallest in the sense no proper subset will give me span which is everything. But let us look at some examples to understand this concept, okay, something to understand. So, examples. I think best is plane itself. So, let us look at V equal to R 2, right, and let us look at B, which was just now we said. Let us look at 0 1 0, okay, 0 1 and 1 0, right. So, L of B is equal to R 2. Is that okay? We just now said every vector in R 2 is a linear combination of this, right. So, what are proper subsets of B? What are the proper subset of B? It has two elements, right. If you want a proper subset, there are possibilities. You take 0 1 or 1 0, right, and if you want to say proper subsets, let us say non empty also. If you are empty, then nothing will be there, right. So, proper non empty, we are assuming that, okay. Now, so call this as B 1 and call this as B 2. B 1 is a proper subset of B, B 2 also is a proper subset of B, right, and these are the only ones. Now, what is linear span of B 1? We want to check is it equal to whole of it or not. What is linear span of B 1? What this is alpha times 0 1, right, where alpha belongs to R, and what is that equal to? So, that is equal to 0 alpha, alpha belonging to R. What is this? This is the x axis, this is y axis, this is the y axis, it is not all of R 2. So, not equal to R 2. What is similarly L of B 1, B 2? B 2 was 1 0. So, that will be equal to alpha 0, alpha belonging to R, right, which is again not equal to R 2. So, that is the sense we are saying it is the smallest. So, that means what? That if I look at this B, it has the property L of B is span of B is whole of R 2, and even if I cut one of the elements, that does not span whole of R 2. So, we will say, so hence B which is equal to 0 1 1 0 is a basis for R 2. This is a basis for R 2, right. So, now you understand what is the definition of a basis. It is a set of vectors in that vector space, right. So, that their linear span gives me everything and no subset give me the span as the whole thing, then such a thing will be called as a basis of the vector space. So, what are the questions one would like to answer? So, here are the questions we would like to answer. So, the questions, okay, before even questions, let us look at some one more example. Let us look at one more example, okay, to understand what is happening. Again, let us take V equal to R 2, right, and let me take now the set B to be equal to say 1 0 and 1 1, right. So, the question is is B a basis? Is this a basis of R 2? So, if you want to check it is a basis or not, according to my definition, 1, it should span R 2, right. That means, every vector in R 2 should be a linear combination of these two vectors, and second, if I drop one of them, then I should not be able to get the whole thing, right. Okay. So, let us check. So, first is L of B equal to R 2? That is the question. That means what? So, let us take alpha and beta belonging to R 2 and try to find, say, x and y such that alpha of x of 1 0 plus y of 1 1 is equal to alpha beta, right. That is what it will mean, saying that R 2 can be obtained as a linear span of the vectors in B, right. That is what this means. So, let us check what this means, is it possible or not. So, let us check that. So, that means what shall I be doing? I should be, what is the left hand side, that is, so x, and that will give me x plus y and y equal to alpha beta, right. Is that okay? I have simplified the left hand side, that is, what should be y equal to? Beta, and what should be x is equal to? Alpha minus beta. So, given alpha beta, we can find x and y by this equation by star such that x times 1 0 plus y times 1 1 is equal to alpha beta, right. So, given any vector with components alpha beta, I can find scalars x and y such that is a linear combination give me. So, implies that L of B is equal to R 2. So, one condition I have verified, right. To check that whether this B is a basis or not, I have verified the condition. What is the second condition? I should verify. I cannot make it smaller, right. So, second, what is B? That was equal to what was B? So, that was 1 0 and 1 1, right. Subsets, proper subsets. What are proper subsets? B 1, that is 1 0, other one 1 and 1, right. So, let us see what is L of B 1. What is L of B 1? That is precisely alpha 0, alpha belonging to R, right. Everybody following? Yes. What is L of B 2? So, alpha belonging to R. These are my spans of B 1 and B 2. What is L of B 1? If you look at geometry point of view, that is x axis. So, that is not equal to R 2, is a proper subset of R 2, it does not give everything. What is alpha? There is a line y equal to x. So, that is again not equal to R 2. So, if I take B and cut any one of the vectors, I do not get span everything. So, hence (1 0) and 1 1. So, this B is a basis. So, what we have done for R 2, we have produced two different bases. One was 1 0 0 1, right, just now we proved that, and now I have gotten 1 0 1 1, that also is a basis. So, what does that mean? That gives an indication that the basis for a vector space need not be unique. You can have more than one basis for a vector space, right, but the property should say it should span and it should be the smallest spanning it, right. You can have more than one possible. In fact, in the in R 2, if you take any two lines which are intersecting, not parallel, not coincident, that means there should be two lines. Any two lines if you take, that will form a basis. That is something saying similar to, it is not mentioned anywhere in books or schools. When you have coordinate system, you always take x axis and y axis, right, and you say everything else can be obtained by moving parallel to x axis and then moving parallel to y axis to reach any point. So, any vector is a linear combination of x coordinate and y coordinate, but why should I take to be perpendicular? I can take any two lines. The only thing would be I should be moving parallel to these lines now, right. So, a coordinate system, that is what coordinate system is, that it should not be perpendicular always, right. So, that is what we are saying, that 1 0 and 1 1, they are not perpendicular, but still they form a basis, right. Advantage of those perpendicular ones is because of Pythagoras theorem and computations become simpler, that is another story. But as such basis, any two lines which are non parallel, right, otherwise it is the same thing basically saying, right, they should intersect, right. So, any two intersecting lines will give you a basis. So, take vector here and take a vector here, right, they will give you a, okay. So, basis we are defined. So, what we have done today is we looked at system of linear equations A x is equal to b. We looked at the solution set of the homogeneous system and said that solution of the general system can be obtained from the homogeneous system, right, by taking a particular one and adding it to the solution of the homogeneous one. So, solution of homogeneous becomes important, and solutions of the homogeneous system we can call it as a null space, and that has a property of being a, that motivated us to define what is a vector space, right. So, null space has the property, if you take two vectors and take linear combination, that is again in the null space, right. So, we defined what is called a vector space, we looked at various examples, and what we are looking at is how to generate a vector space as a linear combination of a subset of it, and we have come to the notion of basis. A basis is a set of vectors by which whose linear combinations of elements of which gives you the vector space, and it is smallest one, nothing smaller will work, right. So, next lecture we will look at how to find basis of a given vector space. Okay.